Assalamualaikum warahmatullahi wabarakatuh. We are from group 18. We want to present about solving differential equation using eigenvalue in RLC circuit. Group members, we have Fatin Nabila, Nurul Atira, Nur Alia Kristina, and Baiduri Janati. And my name is Nur Alia Kristina, with number metric 1230567. Now, we proceed to introduction. An RLC circuit consists of resistor, inductor and capacitor, which is connected in series or parallel circuit. For resistor, it controls the flow of current and dissipates the energy. And for inductor, it stores energy in magnetic field. Last, for capacitor, it stores energy in electric field. The image shows the difference of parallel circuit and series circuit. Now for the next slide, we want to know the application of circuit used in electric engineering. There are 3 examples such as, first, we have radio tuning. It's selecting specific frequency for communication. Second, we have signal filtering. It for amplifying and attenuating signal of certain frequency. Last, we have oscillator and amplifier. It for generating stable signal for devices. Now, we proceed in relation between RLC circuit and eigenvalue. First, behavior of an RC circuit is described by a second-order differential equation. Here is the example of equation. The equation is d square over dt square multiplied by it plus r over l multiplied by d over dt multiplied by it plus 1 over LC multiplied by IT equal to 0. This equation shows how the current I change over time due to the resistor, inductor and capacitor. For solving the equation, we can rewrite it in terms of a characteristic of equation. Here is the example of characteristic equation. L lambda square plus R lambda plus 1 over C equal to 0. The lambda in equation are the eigenvalue, which provide critical insight into the circuit's behavior. Next slide. The roots of lambda of this equation are the eigenvalue, which reveal critical properties. In natural frequency of oscillation and damping behavior, overdamp, underdamp or critical damp. Last, in system stability over time. According to eCampus Ontario, in a RLC circuit, eigenvalue determine how quickly the system stabilized or oscillated. For example, an underdamped circuit with complex eigenvalue oscillate at a frequency determined by the imaginary part of the eigenvalue. Now I pass to the next person to present.
The speaker name Fatin Nabila binti Muhammad Ruslan and matrix number 1230542. So I will explain the methodology. So here's an example of question solving differential equation using eigenvalues RLC circuits. The question is determine the eigenvalues of an RLC series circuit with resistance 0.06, inductance 0.01, capacitance 50 over 89 and voltage source ET equal to 0.1 sin 10t. First of all, we will apply Kirchhoff voltage law, which is EL plus ER plus EC equal to ET. And then we substitute the voltage expression for each component. And then we have L di over dt plus Ri plus 1 over C Q equal to ET. And then differentiate with respect to time and using I equal to dq over dt, and the equation becomes L d square I over dt square plus R di over dt plus 1 over C I equal to dE over dt. Next, we will gonna substitute all the information given using previous formula, and then we got 0.01 d square I over dt square plus 0.06 di over dt plus 89 over 50 I equal to cos 10t. And then to find the eigenvalues, we focus on homogeneous equation, ignore the external forcing term cos 10t, and then we equal to 0. And then dividing through by 0.01, we simplify to this square I over dt square plus 6 di over dt plus 178 I equal to 0. To solve this equation, we assume a trial solution of the form IT equal to E power of lambda t, where lambda is a constant that will be determined. So the first derivative of IT is di over dt equal to lambda E power of lambda t, and then the second derivative of IT is d square I over dt square equal to lambda square E power of lambda t. Then we're gonna substitute into the homogeneous equation, and then we got lambda square e to the power of lambda t plus 6 lambda e to the power of lambda t plus 178 e to the power of lambda t equal to 0. Since e to the power of lambda t not equal to 0, we can divide through by e to the power of lambda t to simplify, and then we got lambda square plus 6 lambda plus 178 equal to 0. To find the eigenvalues, we're gonna using the quadratic formula, which is lambda equals to negative b plus minus the square root of b square minus 4ac divided by 2a, where a equals to 1, b equals to 6, and c equals to 178. And the final answer will be lambda equals to negative 3 plus minus 13i, which lambda 1 equals to negative 3 plus 13i, and lambda 2 equals to negative 3 minus 13i.
The speaker is Baidu Janati Ahmad Aminuddin, metric number 1230575. So I will present about result and discussion of the solution. So the result is lambda equals to negative 3 plus minus 13 imaginary. The first one is damping. Negative 3 represent the exponential decay, indicate that the oscillations gradually decrease in amplitude due to resistance. So the real part is negative 3. So this real part determines the rate of exponential decay of the transient response. In this case, and negative 3 indicates that the transient oscillations will decay exponentially at a rate proportional to e to the power negative 3t. The decay is caused by the resistance, which dissipates energy from the circuit. Next is oscillation frequency. 13 imaginary correspond to the oscillatory behavior. This frequency depends on the inductance and capacitance. The imaginary part corresponds to the angular frequency of the natural oscillations of the circuit. Volt equal to 30 rate per second represents the circuit's tendency to oscillate due to interaction between the inductor and capacitor. So this oscillation occurs at the natural frequency of the system. Next is discussion about physical interpretation of eigenvalues. The first one is negative real part, which is negative 3, ensures stability, no endless oscillation. The larger the negative value, the faster the oscillation decay. So negative 3 represents the energy dissipation in the circuit caused by the resistor. The larger the negative value, the faster of oscillation decay, means if the resistance increases, the real part becomes more negative, leading to faster damping. If resistance decreases, the real part approaches zero, leading to sustained oscillations, which is under damping or instability. The next one is imaginary part, corresponds to the system's natural oscillatory tendency. So this imaginary part indicates the angular frequency volt equal to 13 of the natural oscillations in the circuit. The imaginary part indicates a balance between energy storage and dissipation, resulting in damped oscillatory behavior.
The speaker name is Nurul Atira binti Nur Azhar. My metric numbers is 1230531. Now let's move on to the conclusion. So as we know, RLC circuit, which consists of resistors, inductors and capacitors, are analyzed using differential equations. These equations help model the behavior of the circuit and reveal the crucial insights into its performance. Also, to summarize it, we also have explored how eigenvalues play a fundamental role in understanding and designing RLC circuits. First, we saw the eigenvalues provide deep physical insights into circuit behavior, enabling engineers to optimize circuits for applications like signal processing and filtering. The mathematical foundation, including differential equation, is critical in modeling this system. Last but not least, we examine how eigenvalues determine a circuit dynamic response. As example in the slide, overdamped system exhibit no oscillation but have a slow decay. Underdamped system display oscillatory decay. critically damped system ensure the fastest decay without oscillation. By leveling this understanding, engineers can predict and enhance circuit performance, ensuring stability and efficiency for real-world application. In essence, mastering these concepts bridge the gap between mathematical theory and practical engineering design, empowering us to create advanced and relevant electronic systems. I think that's all from us. Thank you.